In many of my recent projects, I've been leveraging PSoCs, and you'll hear me talk about those time to time in my different videos. At some point early in my 286 build, I talked a bit about PSoCs, kind of what they are, but I thought I'd take a little bit of time and just make a dedicated video to what are PSoCs and maybe how I am using them. By no means am I an expert in PSoCs, but I'm finding parts of their functionality quite handy, and I thought I would kind of provide a little bit of background on that. Back in 2022, it looks like March is when I initially posted this, I had posted a write-up on my blog about using programmable logic devices, or PLDs, and specifically the GAL22V10 PLDs. And I was finding those quite handy to reduce maybe some of my IC counts. For example, on my video card for my 320x240 video card, and that would have been back in my 6502 and my 65816 builds. And PLDs are great, and I've liked those, I've used those, and this GAL22V10 has been specifically one that I've used a bunch. Along with some software called Digital that I've used in tandem with that really make it pretty easy to lay out some logic and write it to those PLDs. More recently, though, I've started using these PSoCs, and that gets me into this programmable system on chip. And so let me start out with maybe what the official definition is from Infineon for what a PSoC is. So it's a microcontroller, and they're calling them the world's only programmable embedded system on chip based on the ARM Cortex-M processor. And really, what it gives me access to are some of these programmable blocks, and like the digital blocks I'm working with quite a bit. And then also can do some stuff with analog, and there's different interconnect routing, and then this what they're calling CapSense, which is a capacitive touch sensing that you can connect different things to it and have touch type of applications. The specific one that I am using is a CY8 CKit-059. I've looked at one of their other kits that I've gotten, and it doesn't really do exactly what I'm going to show in this one. So I'm going to keep this video scoped into or focused on the CKit-059. So if you do go out and purchase some of these, look for that specific kit. And what you're seeing on the screen here is these should be about $15 USD or US dollars. And if I go to Infineon's website and say I want to buy now, basically purchase, it tells me everybody is out of stock. And that has been the case, and most of them unfortunately have a 6 to 12 month lead time yet before they're going to get them. However, I do see them pop up in other places, and I just recently bought a batch of these from Newark. I picked up about a dozen of them from there. They came in stock. There's a few hundred of them. And I think they completely sold them within a couple of days, so they went pretty quickly. So if you are interested in these and you do see them come up, especially at the normal pricing of $15, you might want to try to snag a couple if you can. You can get them readily at higher prices, probably about 10 times that price, $150. I think you can get them pretty easily off of eBay. And I do see some pop up on eBay for a more reasonable $20, $30 from time to time if you keep an eye out. This is what this device looks like, and you'll see that there's really two parts to it. The idea is that you can snap it apart. There's the programming side of it on the left, basically plugs into a USB port and then allows you to program the PSoC to the right, which is the main board. And then it's got all of these different connection pins, basically, that you can solder in for really I/O, just general purpose I/O type of pins. And some of them have some special uses, but in general, you've got quite a few just I/O pins that you can use however you want. And if I go to this website, this is kind of the landing page for this product. And if you just search Cypress CY8 CKit-059, you'll get this page in the top 10. But here specifically is the URL if you want to get to this. And you can check that buy online periodically to the right and see if anybody has them in stock. There's also a user manual that you can click to the right, which is pretty good. And I found with this entire kit, all the stuff here in these Infineon plus Cypress that they're showing products, really the documentation is good, the samples are good, the software that controls it is good. I've been quite happy with everything. Really no concerns at all. Maybe diving into this a little bit more, here you can see some of the pinouts, which again aren't super important. Maybe so one thing I would notice, a lot of the stuff I'm doing, I avoid any of the pins that have capacitors on them, and they note that here with this asterisk. So any of these pins with the asterisk, you're going to want to stay away from using those if you're doing any high-speed type of stuff. That's probably more for your sensing applications, things like that, which I'm not using. I'm doing more decode logic like you're seeing over here that I'll talk about in just a second. And in the actual chip on here, this PSoC chip is this one here. So specifically, probably can't read this in the recording, but it's a CY8C5888LTI- or LTI, yeah, LTI-LP097. Anyways, that's the actual PSoC chip, and they've just put it into this breadboard friendly package. From that package, then I've got a little USB port that I can use and connect USB devices to it. I've got this USB over here to actually program it. If I snap it apart, I can put little pin headers and just connect here with a simple cable when I need to do programming. Now I've done a little bit of work with little breadboardable FPGAs, similar in size, and they're great and all, but all the FPGAs I've found, well, I shouldn't say that. All the ones I have used and been able to get my hands on are all 3 volt. And as I'm doing all of this 286 or 65816 or VGA type of stuff, I'm pretty much just working in a 5 volt world. And so I really appreciate that this product lets me go up to a 5 volt. So I can feed it 5 volt for power, all the signals in and out, 5 volt based basically. So that is really handy. One of the reasons I'm really using this, though, is really for rapid prototyping so that I can quickly prototype some ideas. I don't have to get out a whole bunch of discrete, ICs, inverters, and 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 NAND and OR and NOR gates and all of that stuff and try to build up some logic. I can just quickly build it out in the software, program the PSoC with it, and then test it and adjust it accordingly. And then at some point, once I get the logic figured out, then I can go and actually pull out the real 7400 series HC chips, for example, and build up a comparable circuit. Another benefit to this, though, too, is even after I have it in my system, I can come back and change things around. Maybe change logic of how I'm doing address decoding or add additional I/O capabilities to my system and not have to do a lot of rewiring or building new PCBs as I go. And 3 specific examples of where I'm using this. On my 286 system, I'm using it to do decode logic. On my VGA card, my most recent 640 by 480 VGA card, I'm using it to generate all my sync signals, to generate all of the video address signals, and then also do some decode logic on the video card so I can flip between 2 different frames. I have 2 frames of memory that I can switch between. 286 will access one frame and my video output will access the other frame, and so I have some logic to let me control the proper access to that memory, which is just standard single port memory. What you're seeing on the lower part of this screen on the right is this software that they have, and again, this is really meant to just be a thumbnail here, but their software seems to be quite intuitive, and they have nice links to the data sheets and everything as you go through this, so it's pretty easy to use from what I've found so far. And so here's a picture of my 286 system on the left and a video card that I'm working on the right. And you'll see that on the 286 I've got a PSoC just put right onto my system board. And at some point, maybe I'll take that away and actually put on discrete chips, but I'm finding it so handy just to be able to change and adapt my system. For example, if I want to add a brand new I/O port for some new I/O device, it's easy for me to just go in and quickly program that PSoC, maybe run a couple jumper wires, and now I have access to some new devices without having to rework a lot of stuff. On my video card, you can see I have a pair of PSoCs. Again, one is doing this frame decoding for my VGA, or basically logic, address decode type logic. And then the other one is generating all the timing and addressing for my VGA circuit. When I get into the software for this, they have basically an entire library of things that you can pull from. So you can come in here and say, okay, I want to use an AND gate or a NAND gate or a flip-flop or whatever it might be. And you can actually just drag those out and connect things graphically. And this is what it starts to look like. And these are just some samples. This would be my 286 logic. This is part of the logic used in my video card. This is actually just the horizontal signals, horizontal sync, and that part of my addressing. And then here's another example that gets into the decode logic on my VGA card. But if I look at that 286 decode as an example, when I look at it, if I was to build that out with discrete components, in other words, 7400 ICs, I would have about a dozen ICs to represent what I have there. So there's definitely nothing complicated in the logic on the screen. This is all really basic stuff. But instead of a dozen, 16 pin or 14 pin ICs, I just have this single breadboardable PSoC that I can put onto my system. And as I change my mind about address decoding and I want to move those things around, I can come in here and just flip a few little values on some of these NAND gates as an example and have totally different decode logic if I want it. And likely don't have to do any wiring changes at all if I want to change that logic. So that is a benefit here. It's easy to change the existing decoding or add additional logic as I go working on my 286. And my 286 still isn't at a point where I'd say it's even near done, so this is still handy to be able to be changing these things whenever I feel like it. Here's an example of the logic I used back on an older video card I did. It was a 320 by 240 video card. And this was to generate all of the sync signals like VSync and HSync, and then also to generate all of the addressing signals for accessing my video memory. And so there's just a bunch of counters here and a bunch of NAND gates and flip-flops and things like that. But basically this was generating all that logic. And that was 22 ICs that would be comparable to. So if I want to build that in discrete ICs or with discrete ICs, that would be 22 ICs I would need, at least the way I've got it laid out. Maybe that can vary a couple depending on how you implement it. But this here is 22 ICs worth. Well, at some point, I decided to get rid of some of those ICs and use those PLDs, programmable logic devices, and that cut it down to this. So now I was down to 8 ICs to get the same functionality. And those PLDs work great. The software that I use, that digital, it's called digital, that software lets me just easily lay out the logic just with gates, drag and drop and connect the wires. Or I can even import an Excel spreadsheet that has really all my logic and a truth table essentially of what I want to see for output, and it'll generate all the appropriate gates for you. All that can be done in digital. It's really easy, and so that then lets me program these PLDs. Well, if I look at the PSoC version, now I'm down to just a single item, a single PSoC, and I can do all that logic. And that's what I've done on my 640 by 480 is I put all of that logic into the PSoC. And I could, of course, break that out into either like 8 ICs here using the PLDs or 22 ICs if I don't use PLDs. For now, my VGA card is leveraging this PSoC. When I go into the software for these PSoCs, here's just an example of some of the stuff. I just try to grab some real quick snippets to kind of show you the variety of things that you can come in here and work with. And there's a whole bunch of analog stuff. I'm not doing any analog. There's a whole bunch of communication stuff, which I'm probably going to try to start using some of that later. I see that there's some nice SPI stuff. There's some I2C support. There's also some USB. And I'm going to see if I can maybe, for example, build a host, a USB host, so that I can plug a mouse into it and then connect from my 286 to that mouse through SPI. So it's an SPI to USB type of conversion. I don't know if I'll actually get that done, but I'm going to try and see if I can do that with one of these PSoCs. In this column, the third column here, it says digital. Here's all kinds of just digital functions, and you can see there's this entire logic section here. So this is really what I want to use the most of. So just plain old AND gates, NAND, NORs, NOTs, ORs, exclusive ORs, NORs, etc. And so I can just drag those out onto a canvas and connect them up and assign which pins on the actual breadboardable prototyping little board connect to my logic, and then start testing it out. You can see to the right, the last column there, there's also support for a lot of your standard basic type of displays. You've got pins to have inputs, outputs, or in-outs, and then there's some other things that look pretty interesting that I'm not using, like connecting to external memory. There are clocks, which I'm using some of that. But just a lot of neat stuff here that's all down in this little PSoC device. Plus, the PSoC can do programming, and this reminds me of working with some of the FPGAs. So I can go into those PGAs, some of those FPGAs, and actually do programming and burn that to the FPGA. This seems like it's something similar, and I've not done any of this yet with these PSoCs, and probably will need to when I get into this USB SPI type of stuff. But for everything I've been doing up to this point, where I want to just quickly draw out some logic and test it, basic logic, just in replacing logic ICs, I don't use this at all. But this is there so that you can programmatically now manipulate and work with those things. And I thought what I would maybe do is jump in here and show you the editor. And what I've got capturing here is just, this is just my system, but I'm going to just kind of set that off to the side and kind of show you how I'm going to start getting into this. So first things first, you got to get a hold of some of these. And like I mentioned, I went ahead through Newark when I saw them pop into inventory, and I grabbed 11 of them. And I grabbed 11 because the 11th one got me free shipping. So it ended up being, $15 each, and anything over $150 gave me free shipping. So I now have a stack of these that I can work with in upcoming projects. And if I take a look at one of these, the kit is, really just this here. And I guess there is a revision. This is Rev D. I don't know if the previous ones I have are Rev D. I think I've got a couple Rev Bs. Maybe I have some Rev Cs. I'm not sure, but this is a Rev D. And as I look at this, this looks pretty much like the ones that I have sitting over here. So I'd have to check and see where on this do they even mark the revision. It might be on the back side. But I could compare and see if I've got, if these happen to be the same version as what I just received. But physically, I'm not seeing any differences just as I look at it real quickly. So this looks to be the same revision as the most recent ones I've been using. But the way this works then is I'd come in here, and I'm not going to do it right now, but I would break this in half. So I'd snap this in half, and then I'd solder in breadboard pins here, and then also on the programmable header here and the PSoC, the main board header, so that I can program it whenever I want and only need this part of it in the circuit. But I'm going to set that aside. I've got another one I can work with already. So this one, I've done that soldering. I've got the pins, basically all my pin headers put in. I've got this up here so that I can do the programming. And then, here's the programmer part of it. So just a little header, I grab my wires like so, and I can go ahead and connect that up, something like this. And then I need a connection to my PC for USB, and so here's my USB connection, and I just simply can plug that in, and now I'll be able to program this PSoC. And so let me open up that software here real quick. And there's just a few projects I've been working on. I maybe will start with just showing you this 8286 build. So this is the logic for my 286 address decoding, the logic up in this PSoC up here. And basically when I get into this, I can look at the design of it. And so this design I can set up, basically I'm just setting up input pins over here. So I say bring in, and there's a little note on the pin. So on 12.0, so on here, there are identifiers for every pin, and 12.0 happens to be right here. So that's 12.0. That says 12.0. I want to bring in my A6 address 6 address, and then I'm going to call it net underscore A6. I'm also going to provide an inverted version for my system here. So I've got a net A6B, B for bar, or basically an inverted version. And then I can come off to the right and I can start saying things like, okay, if my address A7 is 0, 6 is 0, 5 is 0, 4 is a 1, 3 is a 0, 2 is a 0, and this net IO is a 1, then go ahead and send out, a low signal here and send out an inverted signal so I can turn on an LED. And this just happens to be if I'm writing to my IO controller, or sorry, my interrupt controller on my 286, I'll get an LED that will indicate that I'm writing a configuration to it. But I've done that here for my math coprocessor and for my PPI, or programmable peripheral interface. I also have it for my VIA, which is down here doing all my SPI communication. But this is just giving me my IO decode addresses. And up above, I've got some others that help me understand, am I doing ROM or RAM? And am I doing output or writing? So am I reading from RAM or writing to RAM? And I have some logic that goes in with that. And all of that's to support some address scheme that I've said I'm going to use on the system. And this is actually the current address scheme that I am using on my 286. So I have RAM that starts at 0 and goes up through 9, FFFF. And then once I get to A, that's my video. I skip the B, I'm not using it right now. And then the C through the rest of my 1 meg is my ROM. If I go and maybe open up this VGA, I'll just show you what that looks like real quickly. In this VGA circuit, I've got a couple sheets here, 3 sheets, but here's the first one. And what I'm doing in this one is generating the address signals, part of the address signals, so that as my VGA is going through the screen, it knows what data to fetch for each pixel, so what color data. And so this is going to generate part of my addressing. It's going to also generate my H-sync and my H-blank signals. And that's all really done just with a counter. So I have a 10-bit counter here that just counts, and then I check for certain values. And if I hit those certain values, then I maybe flip something and say, okay, that was H-sync or that was H-blank in the timing of how I'm drawing my video screen. And here's part of the addressing, so that as it's rotating through all those numbers, I know which color data to pull from whether it's a ROM or from, in my case, my video memory, the RAM. So that's the horizontal. Then I do the same thing. I've got something similar for my vertical to generate VSync. And those VSync addresses, or vertical addresses, all the horizontal addresses plus vertical addresses is what I use to access addresses in my static RAM for my video card. Maybe a third example then I could pull up real quick is just the VGA, the decode logic that I'm using. In this one, you see a lot of the same things. I got some addresses I'm bringing in. There's a bunch of kind of standard 286 type of statuses that I'm going to use to know the status of, am I reading or writing IO? Am I reading or writing memory? Am I reading a low byte, a high byte, or both low and high byte, etc.? But then in this, I have basically logic that's going to let me flip and say the 286 gets one frame or the other, and the VGA output gets the opposite. And that way there's no contention issues, and I can programmatically, by just setting a register value from my 286, flip which frame of memory the 286 has access to and which one, therefore, the VGA output has access to. And really the only thing different in here that maybe shows up that's new is this, which is a multiplexer. So I can basically say, here's my pin that's going to control which of these I pass through that multiplexer, option A or option B type of thing. Maybe what I'll do for now, though, is I'm just going to open up another project that I have here, which is I just call it Scratch. It means really it's just a temporary one that I'm not too worried about what's in here. Here, for example, with some simple logic at some point I was starting to lay out, and so I'm going to take in 4 address signals. I'm going to invert one of them, invert another one down here, run those into a 4-input NAND gate, and then kind of work my way over and generate video 0 low or high, video 1 low or high. So some type of enable signals that at some point I must have been experimenting with. Now the way this gets set up, I build this, and then I'll eventually come over and say, well, which pins do I hook all of those things up to? So that's where I start going through this PSoC device, and I pick which pins do I want to use. And as a reminder, I make sure I avoid the ones that have capacitors on the external side of them. And that's back in the documentation, but I can come in here and say, put this on P16, this on P17, and I can just work my way through. And just because there's something in these others doesn't mean I can't use them. The ones I can't use are grayed out, and once I use them, it also helps me kind of keep track of that by changing them blue, so I know which ones I'm using in my design here. And I'm just arbitrarily picking these. It really doesn't matter right now. Okay, but once I get those all in, I've now said these are the corresponding pins here that I want to tie to those different input or output signals that I built over here. And then at that point, I typically would save it. There's a button here where I can say build it, and I can just wait and see if I get any errors. And like in this case, it looks like I did. It said, okay, yeah, you've got something wrong over here. And that was probably just a drawing issue. Sometimes when I copy and paste or move things, I don't hit things exactly right. So then I just kind of work through this and see if I can correct all the issues. So it doesn't like something there. It says it requires a connection when it is visible. And so something in this. And maybe I'll just start a new one here in a second if maybe might have been up there where the problem was. Okay, yeah, so now I see a dot. It's probably connecting that. So now let me try building again. And it looks like that's going through. So then this will get through and saying, okay, you successfully built this. And so now then the next thing I can do is go ahead and program the device. So if I actually wanted to put that onto this device, I would just plug it in. And let's make sure I get this plugged into USB. I do. And I've got power indicators here, so that's looking okay. And now I can come in here and just say program it. And usually the programming goes pretty quickly if I've already built it. So at that point, this is now programmed with that I just went through. Now, if I want to start from scratch though, and let's just say I zoom back here and I just delete all of this, this is what it's going to look like when I come in fresh. And if I want to start building out some logic, I just come over here and I grab these components and I drag them out. So if I want an inverter, I can come over here. If I want some input pin, like a digital input, I can drag it out. So I'm going to have some pin, I'm going to invert the signal. Maybe I'll have another input pin, so 2 pins. And I'll go ahead and connect this pin directly here, the inverted version of this other one here. And then I probably need an output pin, and so I drag an output pin and connect that up. So simple logic, and it's automatically assigning, or it did, at least with here, 2, 1, 1, 2, it grabbed assignments for that. I probably would come over to my pins and look at that, make sure they're actually on pins that I want. So maybe I'll use pin 1.2 here, and then I'll do 1.3. Okay, 1.3 must be used by something else down here, my JTAG, so I'll just pick 1.6. At that point, I will save it, and then I'll just program it. And so at this point, it's going to build it and program the device all in one shot. And then I've got 2 input pins I can now actually plug something into, and then 1 output pin that's going to go through whatever logic I just got done building, which again is kind of arbitrary logic at this point. But you can go through this list and there's all kinds of things. You just drag them out. For example, if I wanted to do a flip-flop, I can take this flip-flop and just drag it out. When I double-click it, I can configure it. And if I hit datasheet, it will open up the datasheet for that so that I can read through how does this flip-flop work, what settings can I set, etc. And maybe I would get out of that. If I want something, let's say a counter, I can go find where's the counter. If I don't know where it's at, I can just come up here and say search for, I'm looking for a counter. and then that should find it. So it looks like I've got a basic counter, and then there's a down counter, and then there's also this counter function. So I have to figure out, well, which one of these am I actually looking for? And I think I'm looking for a basic counter, but if I had pulled this one out, it tells me, okay, this is an 8, 16, 24, or 32-bit counter to count events. Well, I don't want to count events. What I want to actually do is maybe count up. So I would grab this one. Then I would go in and say, well, how many bits do I want to count up? And if I was doing my video card, for example, I think I have 10 bits on that. And then maybe there's some other settings, which not much here, that I'm going to play with on this one. And I say, okay. Or I can go again, look at the data sheet and figure out how to use this counter. But now I have a counter. And maybe I could do something simple like this. I've got a counter and I want to enable that. And so there is, I believe, a constant I can use. So a logic high, I'm going to tie that to my enable. The reset, I'm going to tie to a low. And if I want to validate the active high, active low type of stuff, I could go back to the data sheet and I could look up and just see, okay, reset. This input resets the counter value to 0. A little sensitive. Okay, so I'm just looking to see if they say high or low, but I think these are all active highs unless they indicate otherwise. I'm going to go with that assumption for now and not spend a lot of time on it. Then I've got a clock. I've got to give it some clock source. And so I can go in here and search for clock. And there's a clock down here. And I can go put that in as my clock source, just connecting that up. And again, I can configure that and set a frequency and a tolerance. And let's just say I bring this way down 12 hertz. And maybe actually let me go 1 hertz if I can. Now if I look at the PSoC, there is a built-in LED, and that LED is also tied to pin 2.1. So I believe I can just go in here and say, okay, look for an output pin. And so I'm looking for a digital output pin right here. And when I go over to my pins, that output pin I'm going to set on 2.1. So there's my 2.1, and I'll save all of that. So now I have this counter is actually going to send out, it's basically going to count up. I don't want to just put that pin there, so let me cut that for a second. I'm going to see if I can compare. I'm also going to look at the counter and see, yeah, there's nothing else there I can work with. So I want to go ahead and see if I can do a compare. And I was thinking there was a comparator. So there is a digital comparator. And it looks like I can compare two values. And so maybe I will go in and look for a constant. I'm going to change this down to an 8-bit counter, just so it's not so big. And maybe I say that when it gets to 200, I want that LED to turn on or something like that. And maybe just to make this go faster, I'm going to say it's a 4-bit counter. And I've got this compare output. And here I'm going to tell it I'm looking for a 4-bit. And I'm going to go back and look at a constant, digital constant. And then I can go into this and say, okay, when you hit a certain value, let's say you hit the value, let's say 9. Then I want to see this flip. And I'll go ahead and connect that to there. And so I've got a counter. It's a 4-bit counter, so it'll count from 0 to 15. I'm going to always have it enabled and never reset it. And I'm going to hook it up to a 1 hertz clock, so once per second. And I'm going to compare the output of that counter to the value 9. And when they do match, I should then get a light up on my little LED. So let me just build that and see if I've got any problems with it. and it says I've got something that's connected to a much bigger width, and that might have been this wire that I had previously connected. So I'm just going to delete that for a second, because that should be a 4 to a 4. This was a 4-bit counter, and this is a 4-bit there. Oh, this one here, I got to tell it it's only a 4-bit constant. And let me try that again then. So I'm going to go through here and try this again. Okay, so it did give me some warning about the accuracy. It's saying I can't keep it exactly within 5% of 1 hertz, which I'm telling it I want to be between 0.95 and 1.05. And it's telling me it can't quite be that accurate. It's going to be between half and 2, and that's fine. I don't care. That's accurate enough. If I was worried about it, which I had to do on my VGA card, I then on my VGA circuit put a separate oscillator that I feed in, so I can do a very precise oscillator on this. I'm going to go ahead and program that. So I've still got my power there, and let me do a program of this. And at that point, this should be running, and there it lit up and there it went off. And so it's doing a count right now. It's counting from 0 to 15, and every time it gets to 9, we're going to see that light up for that one period, that one second basically, every time it's at 9. And if I wanted to, I could say, well, I want that to go faster, and instead of, let's have it go, I don't know, 10 times faster, 20 times. So I'll go 20 hertz, and I'll go ahead and program. And I'm just doing this so you kind of see how you go through the process. You build it out graphically, you build it, you program it, and now you're going to see that is going 20 times faster. So you see that quick LED flicker. All I did there is I grabbed some inputs, which are all within the system. If I wanted to hook up a button instead, and they do have a button built in that you can also use. So there's an LED, there's a button, or of course I could hook up something to the pins that go into it. But that's about it for this software. And maybe something else I can point out, back in that programming side of things, I would come down here and start doing C type of programming. So if I wanted to, I could do something down here, and they give you different things like with this clock, things that I can do with the clock programmatically. Again, I've not messed with this, but it looks similar in concept to some of the FPGA system on chip type of stuff that I've done in the past. And that is just a very minor amount of stuff, but this is looking very similar. So I can programmatically manipulate the things that I've been drawing out over here. So for me, these little devices at $15, even in some of those cases like the VGA logic, for me to go in and grab 22 different chips, I'm going to spend as much money on those chips as I am on this little PSoC, if I can get my hands on these PSoCs at regular manufacturer price. Now, maybe in some of my designs, you would say I'm kind of cheating. Back in a 286 system, you wouldn't have had a PSoC back in that era to work with. And yeah, that's true. So could I break this out into separate ICs? Yeah, I definitely could. But my goal with the 286 build is not to do basic address decoding. I kind of have a good feel for how to do that. I'm more worried about, can I work with the 286 and the bus controller and the math coprocessor and all the things that come with the 286 build. And for my video, I'm not worried about the simple things of generating the video sync signal or doing address decoding again up here. I'm worried about all the rest of this complexity. Can I learn that as I go? And so I'm taking the easier stuff, I'm simplifying it down to these PSoCs. Maybe at some point it would make sense to put PLDs in, but I would have the same argument. That's kind of the same level of cheating. Or maybe I go all the way back to independent ICs, and it would end up being a lot of ICs to cover. Again, this was 22 or so ICs equivalent. This one here probably would be, I don't know, but at least a dozen, if not a couple dozen. And so that would make this a much larger circuit. If you have any questions on PSoCs or feedback on this, feel free, post down below on YouTube or over on, I'll put a complimentary blog post page up just for collecting feedback and maybe putting links to some of these different things, or as I learn more about PSoCs and find interesting things about them, I can share it up there. This is a pretty long video, so thanks for hanging in there, but I thought a lot of good stuff here, and I'm really liking these. And like I said, if you can get your hands on some new ones and you like what you're seeing here, try to fetch some. If I do see them come in stock, I can also put an update at the bottom of the post for this specific blog post that I'm going to put up here. But that's all I've got for now. Thanks.